Okay, thank you very much. And let me start by thanking the organizers for the opportunity to present this talk, which is based on work done in collaboration with Paolo Di Vecchia, Rodolfo Russo, and Gabriele Veneziano. So the idea for this presentation is to illustrate some lessons that we can extract from scattering amplitudes about this gravitational wave frontier and from the two-body problem in general relativity, and that have to do essentially with two techniques that we can use to extract information from amplitudes. One is the Eikonal exponentiation, which is by now a well-established method to extract the classical limit of the amplitude. And the other technique has to do with soft theorems, so with relations that link amplitudes that differ by the emission of massless particles, massless modes in the very low energy regime. So the idea is to start by presenting a bit the status of the Eikonal at 3 p.m. and in particular illustrate a shortcut to obtain the so-called radiation reaction effect for the deflection angle for the Eikonal at 3 p.m. using the soft theorem. So essentially this will be the first lesson I would like to convey. And then again, from the soft theorems, we are going to learn something about the zero frequency limit of the energy emission spectrum via gravitational waves, and again somehow this quantity will force us to use the soft theorem in a way which is a bit more refined essentially compared to the first point. And in the very last part, I will instead focus on a couple of observables associated to this zero frequency limit of gravitational waves that force us again to look a bit again more deep into the form of the soft theorems, in particular to specify how really the pole at omega equal to 0 is approached. Now let me start a bit by essentially fixing the notation and talk a bit about this post-Minkowskian black hole scattering that one is usually dealing with when extracting information from amplitude. So we are looking at a regime in which the Compton wavelength of these black holes, h bar over m, is much smaller than their typical size, which is characterized by the Schwarzschild radius, so that quantum effects are negligible. And we also want to look at regimes in which both these length scales are much smaller than their typical separation, which is sized by the impact parameter. Now, as I was mentioning, there is a standard technique that allows us to extract information about this regime of black hole scattering from the elastic amplitude depicted here, which is the Eikonal exponentiation, and that takes this form when expressed in terms of the impact parameter and the center of mass energy squared for the collision. And the usefulness of this 2 delta that appears here at the exponent is that we can simply take derivatives of its real part. In particular, the derivative with respect to the impact parameter itself gives us the momentum transfer for the full classical process. So in particular, this big Q is a classical quantity. Here I'm illustrating it for the 1 p.m. case. So this is the 1 p.m. Eikonal, and its derivative eventually gives the expression for the full 1 p.m. Deflection in the classical process. And this is much bigger as this small q, whose typical size is instead 1 over b, or more precisely h bar over b. And so, as you can clearly see, the ratio of these two is proportional to gm squared, which is again a classically large quantity compared to h bar. So here is the expression for the 3 p.m. Eikonal. This expression has been first derived in this paper here, building on work done earlier by Damour and even earlier again by us in N=8. Anyway, what I would like to focus on is the fact that two types of terms enter this expression. One set of terms is those associated to conservative effects, and instead these terms here in blue, I will use this shortcut to denote this specific expression of sigma, which is essentially the relative Lorentz factor of the two black holes. These terms in blue are the so-called radiation reaction effects, and they're due to the fact that the black holes emit gravitational waves, and these back react on their trajectories, making them deflect a little bit more compared to the conservative setup, essentially. And the first main message I would like to convey is that one does not really need to calculate the full expression in order to learn about this blue piece. Instead, it's easier to extract this from the imaginary part of the Eikonal. So this 2 delta comes equipped with an imaginary part, which gives an infrared divergent exponential suppression to the elastic amplitude. And although this sounds a bit far-fetched. It's instead quite a bit useful, and the reason is the following. So if we look at this imaginary part of delta, we see that in its belly it has a logarithm of this sigma squared minus 1 and also a minus 1 over epsilon, this infrared divergent piece. And they both come precisely with this coefficient, which is essentially the same as the radiation reaction part of the real part. And let me try to explain why this is the case. So first ingredient to this effect is analyticity, that tells us that if you have a logarithm of this form in the imaginary part, you will also have a pi in the real part. The second ingredient that allows you to target this imaginary part in an easier way compared to the full calculation is unitarity, whereby you can calculate the imaginary part of 2 delta by focusing on this 3-particle cut. And the third ingredient, which is going to be our main leitmotif for this talk, is the soft theorem. So in particular, for the 3 p.m. Eikonal, you can safely focus on the 3-level 5-point amplitude, but in order to look at the 1 over epsilon part, you can also restrict to the soft limit for this red line, which is the graviton, and in this limit, the amplitude, of course, factorizes according to Weinberg's soft theorem. Now, the integral over the angles, in which you can orient the momentum, gives you this function here, which is precisely contains this I of sigma that appeared in the previous slide, and then it is the integral over the frequency up to this cutoff that shows for you that indeed this logarithm and the 1 over epsilon will always appear with the same coefficient. So using analyticity, you know that the logarithm must correspond to a pi, but since the logarithm appears with the same coefficient as the minus 1 over epsilon, you can summarize this by saying that if you really just want the radiation reaction part of the real part of 2 delta or the deflection angle or the deflection momentum, you can just take the imaginary part and multiply it by minus pi epsilon and send epsilon to 0. And this is arguably much simpler than calculating the full Eikonal. Now, these radiation reaction parts are crucial in order to ensure that the full result here, when you take sigma to infinity, so the higher velocity limit, agrees with the massless case that had been calculated in the late 80s by Amati, Cefaloni, and Veneziano. Now, this is seemingly very nice, but again, looking at these soft theorems highlights instead a small puzzle, which is the following, and it was of course already mentioned by Gabriele this morning. So the very same line of reasoning, a very similar one, can be used to extract from this imaginary part of 2 delta another quantity, which is itself observable, which is the zero frequency limit of the energy emission spectrum. So you can really look at the energy emitted by a gravitational wave as a function of the frequency, take this derivative and look at what happens near omega equal to 0. And in this limit, you find this expression for the 3 p.m. for the leading order, which is the 3 p.m. one, which is proportional to GQ, because of course this Q also contains power of G. And now you see that you again have this function I of sigma, and so in the high energy limit, since this I of sigma behaves like this logarithm of sigma, you find this singular behavior here. So there is an enhancement due to logarithm, essentially, if you want, of the energy divided by the mass. And so the massless limit seems to be non-smooth. And so we are not really happy with this. And essentially the reason why we find this apparent puzzle is that we were not using the soft theorem in its full glory. In fact, the soft theorem is a very general result, and at the price of focusing on the very, very low frequency emissions, it actually gives you information that is completely arbitrary as far as the remaining particles, the so-called hard particles of the scattering, are concerned. And in fact, Weinberg himself calculated this W, let's say calligraphic W, which is the quantity that you need to exponentiate in order to resum all the infrared divergences of any gravitational amplitudes that are due to the gravitons. And this takes this very explicit form here in terms of some invariance that you can build in terms of the hard states momenta. And this expression is, again, let me emphasize, it's completely arbitrary as far as the momenta P1, P2, P3, P4 of the particles are concerned. Here, these eta n's are just some signs that tell you if a given particle is incoming or outgoing. And now, as again realized by Weinberg himself, this quantity is again related to the zero frequency limit by this expression here. So, since we have this wealth of information for the zero frequency limit, the only thing we need to do is to understand how to apply this very general formula to the case of our classical scattering we are interested in. And to this effect, it's convenient to try to adapt the formalism based on dress states that has a long history to the case at hand. And this led us to propose this operator dressing of the Eikonal. And this essentially is composed of two pieces. One is the Eikonal phase, so really e to the I, the real part of the Eikonal, and this operator part in terms of that is expressed in terms of the oscillators of the gravitons and of the soft factor. Now, the key point in building this operator is that in this step, the deflection that the particles experience becomes identified with the classical one. So essentially, what you need to do is that you can take the formula in the previous slide and substitute P3 and P4 in terms of P1 and P2 plus or minus Q, depending on which one you're looking at. And this is the result. More in detail, you can use this this operator in order to calculate observables that are associated to the radiation, and also to obtain other quantities of interest that have to do with the soft emissions. For instance, you retrieve the infrared divergent Eikonal, so the full real part plus imaginary part, by taking the expectation of this operator in the vacuum of the oscillators. And indeed, you retrieve that imaginary part of 2 delta is precisely given by essentially minus the real part of this expression. And you can also use it to calculate the probability of having n soft emissions and the average number of soft emissions, which are again related to this imaginary part of 2 delta. And indeed, the zero frequency limit, retrieving, of course, the same result that I was anticipating earlier. So just the Weinberg result in which you substitute the classical deflection. Now, this is the explicit expression for the 2-2-2 process in terms of the invariance written in this way. Again, Q is the full classical deflection. And let me emphasize that this expression is in principle valid even if Q were not small, in a sense. It's just the expression for any classical process. Now, an important point is that since the dependence on the momenta is exact, we can go back to the puzzle we had mentioned earlier. So whereas if you expand this expression for Q much smaller than the masses, which is the standard post-Minkowskian regime, you retrieve the expression that I have written earlier, the one that we had derived by applying the machinery to the 5-point amplitude at the 3 level. You can, of course, take the other limit, the one in which the masses are much smaller than the deflection Q, and of course this gives rise to a different expression. But the important point is that even if you then take the limit of small deflection, so the limit of small deflection angles, you find an expression that does not diverge with the sigma we have in the post-Minkowskian case, but rather develops a logarithmic dependence on the Newton constant, or if you want, on the deflection angle. And in fact, since this expression is exact, you can really look at it and see the convergence radius of the PM expansion itself, which is the Q must be smaller than 2m. So having learned about this observable, now let me mention another couple of observables that one can extract. And to discuss those, I will first have to make a small detour and discuss a little bit what happens to this pole, the 1 over omega pole in the Weinberg formula, when you really want to go to omega equal to 0. So to discuss this point, we essentially want to know how we should regulate the behavior of this amplitude as omega goes to 0, or equivalently, if you want, regulate the behavior of the particle for very large times in the very far past and the very far future. So to this effect, we can really focus on a toy model that is very well known to study memory effects, which is just take this idealized scattering process that takes place in the origin. This is essentially a collection of particles that go straight, collide in the origin with some momenta, P1, P2, up to some number of incoming particles, and then are outgoing from the origin for positive time with some other momenta. And okay, the key lesson that you can extract from this toy example is that if you then take the Fourier transform, you find that indeed you retrieve the same stress energy tensor as dictated by the soft theorem, But in order to do these Fourier transforms, you have to assign some small adiabatic switching, if you want, or exponential suppression in the far past and the far future to the respectively to the incoming and to the outgoing particles. And this dictates for you an I epsilon prescription. And incidentally, this is exactly the same I epsilon prescription that would be dictated by the Feynman propagator, to which you attach the soft line in order to derive the soft theorem itself. Now, equipped with this small improvement of the soft theorem, we can discuss some other quantities, in particular calculate really the expectation of the waveform, of the field itself in order to obtain the waveform. Of course, since we have an expression for the Eikonal operator, which is valid only for very small omegas, this expression for the waveform is only accurate for very large time in absolute value, so or either in the very far past or in the very far future. And indeed, we can take the asymptotic limit of the field in order to obtain the asymptotic waveform, the one that we would observe if some event would happen very far removed from us. And indeed, in taking the Fourier transform that is involved in the final expression, it's crucial to have, or it's important at least, to have an I epsilon prescription in order to fix the ambiguity that would come about when you try to Fourier transform 1 over omega. And okay, choosing the specific I epsilon prescription I mentioned fixes this ambiguity for us and gives precisely these types of theta functions, or step functions. This is essentially telling us that the contribution that you get from the nth particle is only there for negative u if the particle is incoming, and is only there for positive u if the particle is outgoing. And this is nothing but the well-known memory waveform, and reproduces the well-known memory effect. The point of this epsilon prescription, as I was mentioning, is to fix an ambiguity that it is in principle there, but is u independent. So in this specific way of fixing it, we find the same result that was obtained by Damour, in which the waveform, or if you want, the asymptotic value of the shear in the very far past, is a constant in u. As you can see, does not depend on u, and is only the sum over the incoming particles. And then, in principle, there are sublime PM corrections. Now, after having discussed this form up, let me turn to another quantity, which is the angular momentum, which is essentially the last thing we can insert in this sandwich with the Eikonal operator. And to discuss it, let me first quickly start with the case of a massless scalar before turning to the graviton. So this is the expression for the generator that we insert, the generator for the charges associated to Lorentz transformation, which include the angular momentum in the spatial part. Then, of course, you can, each of these oscillators pulls down a factor of this soft factor for the soft scalar theorem. And again, including the I epsilon prescription is crucial, because otherwise this thing would be clearly zero by reality. And these are eventually the relevant integrals that you have, aside from the integration over the directions of the photon. And as you can see, a feature of this calculation is that although we had placed, of course, a cutoff, which tells us above which scale the gravitons we are considering are no longer soft, so our results only apply to gravitons below this cutoff lambda. However, the result after doing this calculation is independent of lambda. So essentially, this tells us that the calculation for this angular momentum localizes at omega equal to 0. So in a sense, it's associated to gravitons with exactly 0 frequency, or maybe more appropriately should be identified with some momentum, some angular momentum loss that is due to field that is stored in the static gravitational field. The analogous expression for the gravitons are for the graviton are this one. So here is the operator, and here is the expression in terms of the soft factor that you can derive. And in fact, this expression only uses the fact that this f mu nu is exactly transverse and symmetric, and so indeed it's identical to the very same expression that was that recently appeared in this paper here in terms of the amplitude of the full 5-point amplitude. And okay, you can then perform the integrals, and again the key point is this integration over omega that I mentioned for the scalar, and this is the final expression. Now, in order to see what we have got, then let me compare it a bit with the literature. So by comparing with the number of results for this angular momentum loss to order g squared, which is obtained by substituting in this formula the deflection, the 1 p.m. deflection, we see that it captures completely the g squared angular momentum. So although we only calculated the angular momentum due to zero frequency gravitons, this gives you the full answer at g squared. And somehow this is these two derivations that I presented for the angular momentum and for the radiation reaction of part of the angle are of course talk to each other, because they give two ways of accessing the radiation reaction part of the 3 p.m. deflection. One of them is based on this technique I was mentioning of taking this imaginary part of the delta and multiplying it by minus pi epsilon. And the other one has to do with this beautiful linear response formula of Bini and Damour. And essentially the two formulas agree because, or I mean, maybe using a causal link between the two is a bit too strong, but essentially the setup I presented reproduced both results, and the two agree because of this relation between the imaginary part of 2 delta and this 2 p.m. Angular momentum loss. Now, actually, as I probably should have emphasized already for the zero frequency limit of the spectrum, the form of the results, so whenever it's expressed in this form for the angular momentum and in this form for the zero frequency limit of the spectrum, is independent actually of the details of the particles that enter the scattering of the hard particles, and so in particular it is also valid when the particles carry spin, provided of course that you input the correct deflection, for instance at 1 p.m. That you get for spinning particles, which of course depends on the spin. And indeed the fact that this formula captures the full 2 p.m. angular momentum loss also for spinning particles has been checked in this paper by Paolo and Francesco. Now, in principle, the formula in principle contains all order corrections in G, but starting from order G cube, of course, there will be also contributions due to non-soft or essentially genuinely propagating gravitons that enter, and so the formula is not so useful any longer. Before moving towards the conclusion, let me also mention that in analogy with what happened with the zero frequency limit of the spectrum, also this expression for the 2 p.m. angular momentum loss exhibits the same singularity at large sigma. So in principle, it's singular in the very high energy limit or in the massless limit if you want. But again, the formula, the complete formula is not singular, and indeed you can take the small mass limit in the same fashion as we discussed for the spectrum, and gives you this nice expression in terms of the deflection angle, or if you expand it for small deflection angle, this gives for you the 2 p.m. Angular momentum loss for the massless process. So in principle, as there has already been some discussion this morning, but this could be a way of trying to overcome similar difficulties that happen for the full-fledged 3 p.m. calculation of the total emitted energy and the total angular momentum in this paper here. Now, before concluding, let me also mention that there are not only spatial components in this tensor, there are also mixed time and space components, which characterize the so-called loss of mass dipole or of energy dipole. And to this order, so to the 2 p.m. order, we find this relation, which was already discussed in this paper here, between this mass dipole loss and the angular momentum loss. And so, amusingly, if you combine this information with the expressions for the mass dipole and for the angular momentum, you find that these two losses linked by this relation tell you that the two particles are equally responsible essentially for the loss of angular momentum disorder, irrespective of their mass. And then, okay, we also find the G cube component, but as I mentioned, probably this is not so interesting because starting with order G cube, there are also other effects that enter. Although I should say that whenever I could, I also cross-checked with some pieces of the expression, and I think they match also as order GQ. Okay, the last point I want to make is that, however, to this order, and even the order before, if I understand correctly, there are some enticing effects that this formula does not capture, and that these are probably due to some remnants of the long-range nature of the gravitational force in 4 dimension, and that have been made apparent in the calculation for the trajectories. So it's not based on calculation of what happens to the field, but really calculating what happens to the trajectories at 2 p.m. in this paper here. And I think we will hear more about this in the coming days. So let me just wrap up by reiterating some of the main points. So, okay, the main point is that the real part of 2 delta to the 3 p.m., if you include dissipative together with conservative effect, is smooth at high energy. And probably I should have added that a convenient way of obtaining this radiation reaction effect is either through calculating the imaginary part of the Eikonal, the infrared divergent part, or the 2 p.m. angular momentum. This Eikonal, soft Eikonal operator gives a unitary description for the soft radiation that is added essentially, that dresses any arbitrary, essentially classical process, and gives a number of useful information, including the zero frequency limit for the spectrum, gives for you this imaginary part of 2 delta, in principle to any order in G, provided that you add the proper deflection, and is crucial in order to restore the smoothness of this quantity at high energy, because it combines the information about the full deflection, not the h bar over b deflection, with information about the spectrum. And okay, it also gives a way of accessing this, if it's provided with an appropriate epsilon prescription, it also provides a way to access this JA alpha beta that is lost by the system due to static field effects. Now, in the future, okay, the most natural thing to try to do is to extend a bit beyond the zero frequency limit. Gabriele did a more detailed discussion of the frequency scales at which we hope to arrive in the future. Of course, also comparing with a very concrete proposal for the Eikonal operator that has been already put forward in that case. And okay, another idea could be to try to target these long-range effects that we don't seem to get in this approach, maybe by looking at the subleading theorem. That could be it could be possible that one learns something from that. And okay, I guess the ultimate goal, as again some of the discussion this morning hinted at, is probably to try to understand whether or not eventually all these techniques are able to tell you how to add the effects that are really due to radiation on top of the conservative results, also to the G to the 4th for the deflection and for the exchange momentum. And I guess that's it. So thank you for your attention.
Thanks, Carlo. You're right on time, so we've got plenty of time for discussion. Questions for Carlo? Yes, I see one.
Hi, Carlo. This is Jiashen speaking. Thanks for staying up so late. Great talk.
Hi. Thanks.
Could you say more about the last point for your future direction? Because as you know very well that from the Bini-Damor approach, it's basically the same formula that goes from GQ to G to the 4th. So at least for the Artin velocity part, it's the same calculation. So I wonder if you can see that from your the IR divergence, the 1 over epsilon, could you see the same pattern goes to G to the 4th as well?
Yeah, okay, I don't have anything very, definitive to say on this point. As far as I understand, the difficulty that would come about with our approach should probably be the same as the ones that you encounter if you try to generalize the Bini-Damor approach, namely that there are probably some quadratic things or some, quadratic irradiation reaction things that, I guess somehow the difficulty should conserve itself. So if the problem is there in the linear response formula, somehow should probably be there also in the other approach.
Yeah, so the Bini D'Amour definitely doesn't tell you the full thing at this order, but at least the odd in velocity part is it covered the full odd in velocity components.
Yeah, I guess we are thinking about it, but we didn't really reach a conclusion on this. Yeah.
Okay, thank you.
Also, yeah, maybe another related point is that, okay, I should have emphasized it a bit more, but a problem, or essentially a thing that this approach does not cover is whatever is related to these nonlinear memory effects. So what we really do in this approach is we take the background hard process, which, okay, the most natural case is to take the 2-to-2 process with massive states, and we dress it with soft radiation, right? But then, okay, we know that starting, I guess, from sub-leading order in the waveform, there will be also things that are not captured by this procedure, because this procedure only captures the linear memory effect. And then the order, there are no linear memory effects. So that could be related to, just because it has the keyword non-linear. So.
Other questions? Looks like Donald has a question.
Hi, Carlo. I was wondering if you see any source of BMS ambiguities in, say, this angular momentum radiation at order G
Yeah,
squared?
thanks for the question. It's a point I had planned to make, but then I glossed over in view of time. So, indeed, somehow all this calculation of the memory and of the angular momentum is very much related to the issue of the dependence of the angular momentum on the BMS frame. And indeed, essentially, I was looking also earlier today at a paper of Strominger 2014, where he is one of the first where he makes the link, between the soft theorem, the supertranslation symmetry, and the memory effect. And then there was a sentence that really stated something like, and then we see that even if the gravitons that we add have zero frequency, they change the angular momentum, but then there was no formula. So I guess somehow you could look at this formula and see that this is the formula that makes Strominger's statement correct. That if you add the soft gravitons to your state, they sort of perform a supertranslation and change the angular momentum, and this is the angular momentum that you get. And in fact, this is also a point that has been made quite clearly by Gabriele and Shashavilkovsky in this paper here, where they really show that the difference between the approach of the Moore, where the asymptotic value of the shear in the far past is given by this thing, differs by the canonical choice that you should adopt probably in more standard GR context by a supertranslation. Indeed, this is a pure supertranslation. And so, to give a more precise answer to your question, is that, okay, you can always perform a supertranslation and set the last part of my talk to 0 if you want.
Thanks.
Any questions from Zoom? Feel free to raise your hand. Yeah, go ahead.
Hi, Carlo. Thank you for the very nice talk. I have like a few confusions. So first of all, I wanted to ask, why is it that you need this dressing of the operators? I mean, like, it's usually done for removing IR divergences, and one would understand, okay, it's nice, it's okay to use it at the level of the sublinks of theorem, but you are using it here at the links of theorem. So why is it that it is needed?
There are several motivations to try to undertake this construction. The first one is that maybe from a conceptual standpoint, it's not very nice that in the first part of the talk we are deriving radiation-related effects from an elastic amplitude, right? So where is the radiation? There is no radiation here. Somehow the point is that the elastic amplitude is so smart that from its cuts, it knows about the radiation, and this gives you the right radiation reaction, radiation reacted angle. But a more consistent framework would be a situation in which the Eikonal does not have this imaginary part, which, as you know, just signals the fact that this elastic process that we're considering is actually impossible, strictly speaking, because there must always be some gravitational radiation. And if you want this construction is the first attempt to have this consistent framework, or I should again mention this this work by Donald and collaborators, where they also have an Eikonal operator that goes along these lines. So this, if you want, is the first motivation, to have an unitary operator, manifestly unitary, as you can see here, that does the job. And the second one, okay, maybe let me ask a question. Why would you say that it's more useful, more interesting to also add the subleading one?
I guess you could just remove, like, divergences at the level of the subleadings of theorem, like, like these sub-ones in construction for, proving the sub-theorems, having like a finite S matrix at the subleadings of theorem.
Yeah, okay, as far as I understand, this construction here only removes these divergences that happen due to really on-shell, if you want, gravitons, right? So in this approach here I was mentioning, you only get this divergent part if you take the expectation on the elastic, or if you want, with the zero graviton state. This is infrared divergence, and it is exponentially suppressed by this imaginary part here. But whenever you add some soft gravitons, then the infrared divergence goes away. This does not take care of all the infrared divergences of the amplitude, but it does take care of all the infrared divergences of the absolute value squared of the amplitude.
Okay.
So, but indeed, I agree that it would be nice to add the subleading ones, also in relation to those long-range effects that I was mentioning at the end.
Yeah, also, well, you mentioned a little bit about the nonlinear memory, and yeah, I wanted to ask, like, at the level of the waveform, I think you should expect to show up at 2 loops, right?
Yeah, exactly.
Like,
So as far as I understand,
does this dressing make the work of including this nonlinear?
No. That's the definite answer. So this really only includes what is due to the soft gravitons that are emitted by the hard lines that you had already put in at the beginning. So unfortunately, since you cannot ask a soft graviton, sorry, did you come from one of the hard states that they already put in, or from something else, then the answer starts to be incomplete at sub-leading order compared to this calculation. So I think this expression here should supplement it by some plus order due to the fourth.
Okay.
To be precise, yeah.
Okay, thank you.
Other questions? So I have a question that may not be directly related, Carlo, but the discussion of these zero frequency limits raised it in my brain. So if I think about the spectrum just of isolated black holes to wave scattering or whatever, the omega equals 0 point is also a branch point, which is then associated with power law in time decaying emission from arbitrarily perturbed black holes. So does those kinds of branch points in black hole spectrums, are they expected to arise somewhere in this scattering of particle approach? And if so, at what sort of order or in what way?
Yeah, I'm sorry, but apparently you're mentioning something that I don't know. So could you teach me a little bit about this branching? Because I really, it's the first time I hear about it, I think.
Oh, well, so if you're considering the calculation of quasi-normal modes of black holes, which you can think of, right, as their decaying spectrum, so it's going to be poles in the green function, the poles in the propagator in the negative complex frequency plane. There's also a branch point at omega equals 0 on top of also some pole that's hiding there too. And that branch point, when you just perturb a black hole in some arbitrary fashion with some transient perturbation, will lead to very low amplitude but very slowly decaying emission, first uncovered by Price, but later understood by many authors. And in the time domain, that branch, the integral around a branch cut from that omega equals 0 point, gives you characteristically power law in time decaying emission. And I'm just curious if that naturally arises in this, or is it extra structure you have to endow these point particles with at some point? I just was curious.
Yeah, no, as far as I can tell, just by the formal analogy, I would say that it's something that they don't see here, or that I haven't seen either in other discussions along these lines. And basically because this is really just the pole in omega, whereas you're mentioning a branch cut.
Yeah.
So maybe, okay, now maybe I'm obsessed with the subleadings of theorems, but the subleadings of theorem does come with the log of omega. So I don't know, maybe that one has a branch cut that could be more similar to the situation you have in mind. But probably it's just my ignorance about the phenomenon you're mentioning that that prevents me from giving a more satisfactory answer. So
it was an out there question, but thank you. I don't know if there's any other comments or questions from the audience on that. Other questions then for Carlo? Well, if not, I think we should thank Carlo again for that excellent talk.